Welcome back to another deep dive. Today, we're going to be tackling this paper called Low-Degree Functions Without Non-Essential Arguments. And it looks like it's going to be a really interesting one. It's delving into the world of perfect colorings, particularly on Hamming graphs.
Yeah, it should be fun. There's a lot of really neat combinatorial stuff and also connections to computer science.
Yeah, definitely.
Yeah.
So before we jump into the paper itself, I think it would be good to kind of set the stage for our listeners. Maybe just a quick recap of what a perfect coloring is.
Yeah, sure. So a perfect coloring, you can think of it as like a coloring book problem.
Yeah.
You have a graph, which is a collection of vertices and edges, and you want to color the vertices in a way that satisfies certain rules. And in a perfect coloring, the rule is that each vertex of a given color has a certain number of neighbors of each other color. So it's like a very structured way of coloring a graph.
Okay, so it's not just about making sure that no two adjacent vertices have the same color. It's about having this like very specific balance of colors around each vertex.
Exactly, yeah. And the number of neighbors of each color is determined by the parameters of the perfect coloring.
Gotcha. Okay, and then the paper specifically focuses on perfect colorings on Hamming graphs. Can you maybe just give us a quick overview of what a Hamming graph is and why it's relevant in this context?
Sure. So a Hamming graph, you can think of it as a graph where the vertices are binary strings of a fixed length, and two vertices are connected by an edge if they differ in exactly one position. So for example, if you have binary strings of length 3, like 0, 0, 0, 0, 0, 0, 0, 1, and so on, each of those would be a vertex in the Hamming graph. And then if you have two strings that differ in just one bit, they would be connected by an edge.
Okay, so it's kind of like a way of visualizing the relationships between these different binary strings based on how similar or different they are.
Yeah, exactly. And Hamming graphs are really useful in coding theory because they can be used to model things like error correcting codes.
Right, because if you think about each binary string as a code word, then the Hamming distance between two code words, which is the number of positions in which they differ, that tells you how many errors it would take to transform one code word into the other.
Exactly.
Okay, cool. So we've got perfect colorings, which are these very structured ways of coloring graphs. And we've got Hamming graphs, which are these graphs that represent relationships between binary strings. And the paper is looking at the intersection of these two things, perfect colorings on Hamming graphs.
Yeah.
Now, one of the key concepts that the paper focuses on is the idea of essential arguments. Can you maybe explain what that means in this context?
Yeah, so an essential argument of a function on the Hamming graph is a coordinate of the input string such that if you change the value of that coordinate, it always changes the output of the function.
Okay, so it's like a crucial bit of information that if you flip it, it completely changes the outcome.
Exactly.
And in the context of perfect colorings, how does that notion of essential arguments come into play?
Well, you can think of a perfect coloring as a function that assigns a color to each vertex of the Hamming graph. So the essential arguments of the perfect coloring are the coordinates of the binary strings that determine the color of the vertex.
Okay, so it's like saying that certain bits in the binary string are more important than others in determining what color that vertex gets.
Yeah, and the paper is interested in constructing perfect colorings that have a lot of essential arguments.
Okay, so they want to create these colorings where a lot of the bits in the binary string matter in determining the color.
Exactly.
Interesting. Okay, so that kind of gives us a high-level overview of what the paper's about. Now, I'm curious to dive into some of the details of their constructions. But before we do that, I think it would be helpful to go over a few more definitions just to make sure we're all on the same page. So they talk about things like eigenvalues and eigenfunctions and degrees. Can you maybe give us a quick refresher on what those concepts mean?
Sure. So let's start with eigenvalues. Eigenvalues are associated with matrices. And you can think of them as like special values that tell you something about the structure of the matrix.
Okay, so a matrix is just like a rectangular array of numbers, and the eigenvalues are these special numbers that kind of encapsulate some information about that matrix.
Right. And the way you find eigenvalues is by solving this equation called the characteristic equation, which involves finding the determinant of a certain matrix.
Okay, and the determinant is just like a single number that you can calculate from a square matrix.
Yeah. And once you solve the characteristic equation, you get a set of eigenvalues for that matrix.
Okay. And how do eigenfunctions relate to eigenvalues?
So eigenfunctions are functions that when you apply a certain linear transformation to them, they just get scaled by a factor, and that factor is the eigenvalue.
Okay, so it's like the eigenfunction is a special function that's kind of aligned with the structure of the matrix.
Yeah.
And when you apply the matrix to that function, it just gets stretched or shrunk by a factor that's equal to the eigenvalue. Gotcha. Okay. And then What about degrees? How does that concept fit into all of this?
So the degree of a function is basically the highest power of the variable that appears in the function.
Okay, so if you have like a polynomial function, the degree is just the highest exponent in that polynomial.
Right. And in the context of this paper, they're talking about functions on the Hamming graph, which are functions that take binary strings as input. So the degree of the function is the highest number of bits in the input string that the function depends on.
Gotcha. Okay. So we've got eigenvalues, which are these special values associated with matrices. We've got eigenfunctions, which are functions that get scaled by eigenvalues when you apply a certain transformation to them. And we've got degrees, which tell you how many variables a function depends on.
All right, I think that's a good foundation for now. Let's take a look at the paper's actual constructions in the next part. They'll be back after a short break.
Welcome back. So are you ready to delve into how these special perfect colorings are constructed? Definitely. I'm curious to see how they actually piece everything together, like the Hamming graph, eigenvalues, and all those concepts we discussed.
Well, the authors start off by introducing this idea of uniform collections of perfect colorings.
Okay, uniform collections.
Yeah.
So are we talking about like sets of perfect colorings that all have some kind of shared property?
Exactly. A uniform collection is basically a set of perfect colorings of a graph where if you look at any specific vertex, the colors assigned to that vertex across all the colorings in the collection are the same. It's kind of like having a box of crayons, and no matter which coloring you choose from the box, you always use the same set of colors, even though the arrangement might be different each time.
Ah, I see. So each vertex gets its own little rainbow of colors. And that rainbow is consistent across all the colorings in the collection. But why are these uniform collections important for constructing these special perfect colorings with lots of essential arguments?
They are crucial because they serve as the building blocks for creating larger and more intricate perfect colorings. You can think of it as assembling a complex mosaic from smaller, carefully designed tiles.
Interesting. So how do we even go about creating these uniform collections in the first place? It can't be just randomly generating perfect colorings and hoping for the best, right?
You're right. There's a more systematic way. Lemma 3 in the paper provides a method for generating a uniform collection from any given perfect coloring. It's like taking a single seed and cultivating a whole field of flowers from it. The idea is to use the structure of what's called an abelian group, which is basically a set with a specific type of operation like addition or multiplication to systematically shift or permute the colors around in the original coloring.
Okay, so we're using this group structure to create variations on a theme, essentially generating a bunch of different colorings, all based on that one initial perfect coloring. That's pretty clever. But if we're trying to create these complex perfect colorings with many essential arguments, why start with just one perfect coloring? Wouldn't that kind of limit the complexity we can achieve?
That's a great point, and that's where lemma 4 comes in. This lemma guarantees the existence of a very special kind of perfect coloring that has certain properties that are super useful for the construction.
Okay, so we have a special perfect coloring. What makes it so special? What sets it apart from the crowd?
Well, for certain values of Q, which is the size of our alphabet, and M, which relates to the number of colors, there exists a perfect coloring with a very specific structure for its quotient matrix.
Ah, the quotient matrix. We talked about that earlier. Can you remind us what that is again?
Of course. Remember, the quotient matrix is basically like a summary of the rules of a perfect coloring. It tells you how many neighbors of each color a vertex of a specific color will have. The special perfect coloring guaranteed by lemma 4 has a quotient matrix with a very particular form, and this specific form plays a crucial role in the construction process.
Okay, I think I'm starting to see the pieces fall into place. We've got these uniform collections, which are like sets of variations on a theme, and we've got this special perfect coloring with its unique quotient matrix. But how do we combine these two to create something even more impressive?
That's where Theorem 1 steps in. This is the heart of the paper's construction process. The theorem explains how to take a uniform collection of perfect colorings and combine it with that special coloring from lemma 4 to build a larger, more complex perfect coloring that's essentially dependent on all its arguments.
Whoa, hold on a second. That sounds like a lot is happening all at once. Can we break that down a little? How do we actually go about combining those different parts?
Imagine we're building a house. We start with a blueprint, and that's our special perfect coloring from lemma 4. Then we have a set of prefabricated modules representing different parts of the house, like walls or a roof. These modules are the perfect colorings from our uniform collection. Theorem 1 gives us the instructions on how to assemble these modules according to the blueprint, making sure that the final structure not only stands complete but also depends on every single element.
So we're not just randomly sticking these modules together, we're very carefully connecting them based on the rules laid out in Theorem 1, using that special coloring as our guide. And what we end up with is a perfect coloring that's both complex and robust with all its arguments being essential. That's pretty impressive. But it looks like the paper goes even further, right? There's something called Remark 1. What does that add to the story?
You're right. Remark 1 is like a little efficiency tip. It points out that even though the main construction method can create perfect colorings with many arguments, we can often streamline things. We can actually reduce the number of arguments without sacrificing that essential dependence property of the coloring. It's kind of like optimizing the design of our house to use fewer materials without compromising its stability.
Oh, so it's all about striking that perfect balance between complexity and efficiency. I like it. Mathematicians always appreciate a bit of elegance. Now, where do we go from here? We've built this amazing perfect coloring, but I have a feeling the authors aren't done yet, are they?
You're absolutely right. The paper takes the construction even further with Corollary 2. This corollary explains how to apply the construction method from Theorem 1 recursively.
Recursively. Does that mean we take our newly built perfect coloring and feed it back into the construction process, creating a kind of mathematical feedback loop?
Precisely. It's like taking the blueprint of our house and using it to design an entire city,
Yeah.
then using that city's plan to design a whole country, and so on. Each iteration of this process creates a larger, more intricate perfect coloring, with the number of essential arguments growing exponentially.
Wow, that's incredible. We're essentially creating a chain reaction of perfect colorings, each one more complex than the last. It's like watching a tiny seed grow into a massive, sprawling tree.
But how does all of this connect back to Boolean functions? We started this conversation talking about coloring books and blueprints. Now you're mentioning Boolean functions. How do those fit into the picture?
You bring up a great point, and that connection is beautifully illustrated in Theorem 2. This theorem shows that perfect two colorings, which can be seen as Boolean functions, exist with specific properties. And it even provides two different ways to construct these functions, both based on the techniques we've been discussing.
So we can take those intricate colorings and translate them into the language of Boolean functions. That's really neat. What about Corollary 3? What does that tell us? Corollary 3 focuses specifically on a certain type of Boolean function that has a particular density of ones. This density, as we discussed earlier, is basically the proportion of times the function outputs a 1. Corollary 3 says that we can construct these Boolean functions with a specific density of ones and a large number of essential variables using the methods described in the paper.
So we can fine-tune the properties of these Boolean functions, ensuring they have the right balance of ones and zeros and a good level of complexity. It's remarkable how this paper brings together all these different concepts like colorings, graphs, eigenvalues, and Boolean functions into one coherent and powerful framework.
It truly is a testament to the elegance and power of mathematics. And there's still more to unpack in this paper, including its potential applications in areas like coding theory and cryptography.
I'm definitely interested in exploring those applications, but I think we've covered a lot of ground already. Let's take a quick break to let all this amazing math sink in. We'll be back shortly to wrap up our deep dive into this fascinating paper. All right, we're back and ready to tackle the so what of all this. How do these theoretical concepts of perfect colorings and essential arguments actually translate into real-world applications?
That's the really exciting part. This paper hints at some pretty interesting possibilities, especially in areas like coding theory and cryptography.
Let's start with coding theory. I know it deals with making sure data transmission is efficient and reliable, but how do perfect colorings and essential arguments fit into that?
Well, imagine you're sending a message and the transmission channel is kind of noisy. There's always a chance that parts of the message could get corrupted along the way, right? So in coding theory, we develop these clever ways to add some redundancy to the message. So even if some parts get lost or messed up, the receiver can still reconstruct the original information.
So it's like packing a suitcase with extra socks just in case some go missing during the trip.
Exactly. Now think of the essential arguments in a perfect coloring as like the most important parts of your message, the parts that absolutely have to be transmitted correctly. By understanding how to construct perfect colorings with many essential arguments, we can potentially create codes where those crucial parts are super well protected, making the transmission much more robust.
Oh, I see. So we're creating a code where the crown jewels of the message are heavily guarded, surrounded by all these layers of redundancy and error-checking mechanisms. That's pretty cool. Now, what about cryptography? How do these concepts apply to the world of secret codes and cybersecurity?
Well, cryptography is all about keeping information confidential and secure. One of the big challenges is creating encryption schemes that are really tough to crack. That's where the concept of essential arguments and Boolean functions comes in.
Can you remind me how Boolean functions connect all of this?
Remember we talked about how we can represent perfect two colorings as Boolean functions? These functions take a set of inputs, which you can think of as bits, and produce an output, which is also a bit. The essential arguments of a Boolean function are the input bits that really matter. If you change an essential bit, it flips the output completely. But changing a non-essential bit has no effect.
So it's kind of like a combination lock.
Yeah.
Only the essential bits are part of the right combination. Changing a non-essential bit is like messing with a random dial. It won't open the lock.
Exactly. In cryptography, we want our encryption functions to be super sensitive to changes in the input. That means having a large number of essential arguments. The insights from this paper could actually lead to the design of new cryptographic systems where the encryption key is spread out across many essential bits, making it way harder for an attacker to guess the right combination.
So it's like having a lock with thousands of tiny keys all scattered throughout the system. That's a seriously strong security measure. It's amazing how these abstract mathematical concepts can have such real and significant impacts on our increasingly digital world.
It really highlights the power of theoretical mathematics to drive real-world innovation. Sometimes the most unexpected breakthroughs come from exploring those seemingly obscure corners of the mathematical universe.
This paper is a perfect example of that. We started with colorful graphs
Yeah.
and ended up talking about potential advancements in information security and communication. It just goes to show that the pursuit of knowledge, even in its most abstract forms, can lead to tangible benefits for society.
Couldn't agree more. The quest to understand the fundamental principles of math often opens doors to new possibilities we could have never imagined.
Absolutely. Well, this has been another incredible deep dive filled with mind-bending math and inspiring insights. Thanks for joining us, and until next time, keep those brain cells firing and never stop exploring the fascinating world of mathematics. Welcome to another deep dive. Today we're going to be talking about something called perfect colorings of Hamming graphs.
Yeah.
Now I know
Perfect colorings.
that sounds Hamming graphs.
Very complex.
It is.
A mouthful.
It's actually very interesting, and we're going to
Yeah.
break it down step by step.
Absolutely. So
What is a Hamming graph?
So a Hamming graph, think about words
let's-
of certain length, say 4 letters.
Right.
And they use the same alphabet. So A, B, C, and D. So you have words like AAA, AAB, AABB, and so on. And the Hamming graph, what it does is it connects words that differ by just one letter.
Okay.
So AAA would be connected to AAA,
Okay.
AAC, and AAE.
Okay, so it's kind of like a word ladder,
Exactly, like a multi-dimensional word ladder.
but with a mathematical twist.
A mathematical,
Yeah.
exactly.
Okay. Now, what does it mean to color a graph? Are we talking like crayons and markers?
Yeah.
No, not crayons and markers.
Okay.
It's more like we're assigning labels. You can think of them as colors.
Okay.
So each word, each vertex in the graph gets a color. But it's not random, there's a pattern.
Yeah.
And that pattern makes it a perfect coloring.
So there's some kind of rule that dictates how these colors
Absolutely. There's a very specific structure,
are assigned.
and that structure is captured by something called a quotient matrix.
Okay, so this quotient matrix is like a blueprint.
It's a blueprint. It tells you for a vertex of a certain color how many neighbors it should have of each color.
Okay, so it's not just
Yeah.
assigning colors. It's
They're not
making
random.
sure they
Very specific.
fit together in a certain way.
Absolutely.
Yeah. And what makes this, I guess, deep dive particularly interesting is that we're looking at perfect colorings without non-essential arguments.
Yes, that's the really intriguing part.
What does that even mean? Non-essential arguments.
Think about it like this. In language, we often use more words than we need to get a point across.
Okay.
We have redundancies, filler words, stuff that doesn't really add meaning.
Okay.
A perfect coloring without non-essential arguments, it's like getting rid of all that extra fluff.
So it's like finding the most efficient way to color the graph where every color assignment matters.
Exactly. Every color, every vertex, every connection contributes to the overall structure.
Okay, so we've got our Hamming graph, we've got this concept of perfect coloring, and we want to find these efficient colorings. But to tackle this, we need some serious mathematical tools, right?
Absolutely.
Like I see eigenvalues and eigenfunctions.
Eigenvalues and eigenfunctions.
Yeah, it's popping up in our sources. What are those?
They're concepts from linear algebra, and they help us understand the structure of graphs.
Okay.
So think of eigenvalues as kind of a fingerprint of a graph. They reveal its underlying symmetries and properties.
Okay, so each graph has its own unique...
Each graph has its own unique set of eigenvalues, just like a finger pointer.
Set of eigenvalues. Okay. And what about eigenfunctions? What are those?
Eigenfunctions are these special functions that are associated with those eigenvalues.
Okay.
And they tell us how the graph behaves. You can think of it as how it vibrates in relation to those eigenvalues.
Okay, but how do these eigenvalues and eigenfunctions connect to perfect colorings?
Well, for a perfect coloring, the characteristic function of each color can actually be expressed as a sum of eigenfunctions.
Okay, hold on. So a characteristic function that just tells me whether a vertex...
Yeah, it's a simple function.
...belongs to a specific color or not.
Exactly. Yeah. If it's that color, 0 if it's not.
Okay.
And what Lemma 1 in our source is saying is that you can build this simple function by adding up specific eigenfunctions of the graph.
So the eigenfunctions are like the building blocks.
Exactly.
And by combining them
in the right way.
You can recreate the pattern of the perfect coloring.
You got it.
Okay, so how do we actually construct these perfect colorings without non-essential arguments?
Well, Theorem 1 in our source material, that's the key.
Okay, what does that tell us?
It presents a construction process.
Okay.
And it starts with something called uniform collections of colorings.
Uniform collections?
Of colorings.
Okay.
Think of it like sets of colorings that exhibit a consistent pattern. No matter where you look at the graph, they're like multiple copies of the same coloring. Each copy might be shifted or rotated, but the overall pattern remains the same.
Okay, so it's like having a kaleidoscope of colorings.
That's a good analogy.
Each one's unique, but they share the same underlying structure.
Exactly. And the theorem uses a special type of perfect coloring called RM-like codes as building blocks.
RM-like codes?
Yes.
Okay.
And these play a crucial role in constructing larger and more complex perfect colorings.
So we're taking these basic building blocks and kind of like Legos, assembling them in a clever way to
make more sophisticated perfect colorings.
More sophisticated perfect coloring.
That's right. Now, the perf of Theorem 1 gets a bit technical.
Okay, but I think it's worth walking through the steps.
Yeah, agree.
Just to see how it all comes together.
All right, so first, we assume we have this uniform collection of M perfect R colorings of a Hamming graph HNQ with a quotient matrix S.
All right.
We also assume that the first of these colorings depends essentially on all arguments.
Okay, now what does that mean? Depends essentially on all arguments.
It means every letter in our word matters for determining the color.
Okay, so no freeloading letters.
No freeloading letters. Every letter plays a role.
Everyone's got to contribute.
Everyone's got to contribute.
Yeah.
Now, we also assume the existence of a perfect MQ coloring. Of another Hamming graph, HMNQ, with a specific quotient matrix T. And this matrix T has a specific structure. Its entries, sub j sub, are 0 if I is congruent to j modulo q, and 1 if I is not congruent to j modulo q.
Okay, so we've got our ingredients. We've got a uniform collection of perfect colorings.
Yes.
And then this special perfect coloring with this quotient matrix T.
Precisely.
Where do we go from here?
We combine them in a very specific way to create a new perfect coloring of a larger Hamming graph, HQN plus MQ. And the details are a bit intricate. But the essence is that we're using the structure of those RM-like codes to weave together the colorings from our uniform collection.
So it's like taking threads of different colors and weaving a tapestry.
That's a great way to put it. So we're not just randomly stitching things together. We're following a pattern dictated by these RM-like codes.
And what happens? What does the resulting coloring look like?
Well, the resulting coloring also depends essentially on all arguments, meaning every single letter in our expanded word still matters.
Okay, so still no freeloaders.
No freeloaders.
That's good.
And the theorem gives us a precise formula for the quotient matrix of this new coloring. It will be S plus Q1 sup Ci plus Q1MP. Where I is the identity matrix, and P is a matrix related to the densities of the colors in our original colorings.
So we've created a larger,
more complex, perfect coloring.
More complex, perfect coloring, but we still have a precise mathematical description of its structure.
Exactly. we know exactly how it's put together.
Now, what's the significance of this? Where does this construction lead us?
That brings us to corollary 2,
Okay.
which demonstrates how we can create even more complex perfect colorings with specific properties by repeatedly applying this construction.
So we can keep building on this.
It's a recursive process,
Right.
building upon itself.
Okay, and what about the specifics? How does this construction achieve that efficiency we were talking about?
As we add more layers to our color, the diagonal part of the quotient matrix grows exponentially, while the off-diagonal part grows linearly.
Now, what's the significance of that?
It means that as our colorings get bigger and more complex,
Yeah.
we can pack a lot more essential information into them
Okay.
without losing control of the overall structure.
Okay.
The diagonal entries of the quotient matrix capture the essence of the coloring,
Right.
while the off-diagonal entries represent the interactions between different colors.
Okay.
So as we add more layers, we're increasing the essential information much faster than the interaction information.
So it's like we're maximizing the signal
Exactly.
while minimizing the noise.
We're getting more bang for our buck in terms of information content.
Okay, so this is all very abstract.
Yeah.
Can we connect this back to the idea of functions?
Sure. Remember that each vertex in our Hamming graph represents a word.
Yeah.
A function can be thought of as a rule that takes that word as input and
Right.
outputs a color. So the coloring of the graph is essentially a visual representation of that function.
So each word gets assigned a color based on the function's rule.
Exactly. It's like a color coding system for words, determined by the function.
Okay, and I guess the degree of the function
The degree of the function
reflects the complexity of the coloring?
reflects the complexity. A higher degree function
Okay.
leads to a more intricate coloring pattern.
And in the context of Boolean functions, which only have two outputs, true or false,
Yes.
this connection becomes even more significant.
Absolutely. And that's a great segue into part 2 of our deep dive.
Okay, I'm excited for part 2.
Yeah, we'll explore that connection further and see how these efficient coloring constructions translate to the world of Boolean functions and their applications.
I'm ready.
Let's do it.
Let's dive back in.
Welcome back to our deep dive on perfect colorings. We're about to get into the really interesting stuff, their connection to Boolean functions.
I'm excited, especially after that whole discussion about the quotient matrix growing exponentially. It's like we're building a skyscraper of information, each floor a new level of complexity.
A great analogy. It really shows how efficient these constructions are. But before we get into the applications, let's take a closer look at the math behind these colorings, specifically the RM-like codes we touched on earlier.
Yeah, those seem to be doing a lot of heavy lifting in the construction process. What are they exactly, and how are they connected to perfect colorings?
Well, to understand RM-like codes, we need to first talk about error-correcting codes. They're used in communication systems to make sure data transmitted through noisy channels is received correctly.
Right, like built-in spell checkers for data, making sure the message gets through even with interference.
A good analogy. RM-like codes are a special type of these codes with interesting properties, closely related to Reed-Muller codes, which have a rich history and lots of applications.
Okay, but how do they connect to our perfect colorings? Seems like a bit of a jump.
The key is that RM-like codes can partition the Hamming graph in a way that naturally leads to perfect colorings. Remember, in a perfect coloring, each vertex of a given color needs the same number of neighbors of each other color. RM-like codes let us divide the vertices into groups or color classes that satisfy this.
So they're like blueprints for dividing the graph into perfectly balanced color groups.
Exactly. And lemma 4 in our source material actually proves that a special perfect coloring exists tied to these RM-like codes.
Can we get into that lemma? See the specifics?
Of course. Lemma 4 says that for any prime power q and any m that's a power of q, there's a perfect MQ coloring of the Hamming graph HMQ with a specific quotient matrix T. Remember T from part 1.
The one where entries to be j sub are 0 if I is congruent to j modulo q and 1 otherwise. What's the significance of that structure again?
It shows how the colors are arranged. Imagine dividing the MQ colors into Q groups, each with M colors. T's entries tell us a vertex can only have neighbors from different groups.
So like Q color palettes, and you can't have neighbors from the same palette.
Precisely. That's how we get the perfect coloring. And the proof constructs this using finite fields. Are you familiar with those?
I've seen them in abstract algebra, but it's been a while.
A finite field is a set with a finite number of elements where we can add, subtract, multiply, and divide, just like regular numbers. But these operations wrap around, go beyond the elements, and you circle back to the beginning.
Like modular arithmetic, where we're working with remainders after division.
Exactly. And finite fields have some elegant properties that make them super useful in coding theory, cryptography, and more.
So how do they help construct this perfect coloring?
Well, the proof starts with S, a finite field of order Q. We call it F sub sub. Then we consider all the elements of the field F sub 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 sub, where S is a positive integer. It's an extension of the original field with more elements.
Expanding our set of numbers.
Precisely. The proof defines a coloring function D, which takes a word of length M over the alphabet F sub cubs and maps it to a pair. The pair has an element from F sub sub and one from F sub 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 sub.
So our colors are pairs, one for the base field and one from the extension. Like a two-part code for each word.
Exactly. And D is defined to create a perfect coloring with that quotient matrix T. The specifics are some algebraic manipulations, but the properties of finite fields perfectly match the structure we need.
It's like finite field magic, weaving it all together. The proof also mentions the support of one color, 000, forms a generalized Reed-Muller code. What's that about?
The support of a color means all the vertices assign that color, and those colored with 00 form a generalized Reed-Muller code, which is a kind of error-correcting code.
A secret passage between perfect colorings and error-correcting codes.
And it's not just a coincidence. These codes are perfect for building perfect colorings. Codes with similar parameters are called RM-like codes, and partitioning the Hamming graph into them essentially gives us perfect colorings with the properties we need for our construction.
So RM-like codes are the unsung heroes, laying the foundation for these colorings. What about the practical side? Where does this lead in the real world?
Back to Boolean functions. These true or false output functions are the basis of digital logic, the foundation of computers and tons of other tech.
Boolean functions are like the language of computers, determining how circuits behave and how information is processed.
Exactly. And finding efficient representations of them, ones with minimal essential inputs, is crucial for optimizing circuits, making them simpler, faster, and more power efficient. Fewer inputs means simpler circuits, which means less power and faster operation.
So this abstract math has a direct impact on how we design and build technology.
Precisely. And it goes beyond computers. Efficient representations are crucial whenever you're dealing with complex information, data storage, communication networks, even decision-making algorithms.
It's about conveying information elegantly and concisely, just like with our perfect colorings, without non-essential arguments.
Absolutely. In Part 3, we'll explore these connections further, looking at how our construction methods relate to creating and optimizing Boolean functions.
I'm ready for Part 3. This has been fascinating, and I'm eager to see where it leads next.
Join us for Part 3, where we'll delve deeper into the interplay between perfect colorings, Boolean functions, and the quest for efficient representation in the digital age.
Welcome back to our deep dive, the final part of our look at these perfect colorings. It's been really amazing to see these ideas, from Hamming graphs and finite fields, all the way to error-correcting codes.
It is truly remarkable how these concepts, which seem so abstract, actually have such significant applications in many fields, especially when we talk about Boolean functions and digital logic.
You know, back in Part 2, when we talked about how these efficient coloring constructions could actually help optimize Boolean functions, I was hooked. It's like taking elegant design and applying it to how computers talk.
That's a great way to think about it.
Yeah.
And Theorem 2, which we mentioned before, really brings this connection home. It specifically deals with perfect two colorings of Hamming graphs, which, directly relate to Boolean functions.
Right, Boolean functions only have those two outputs, true or false. So it's like assigning one color to true and the other to false, basically making the coloring a visual representation of the function's output.
Exactly. And the great thing about Theorem 2 is that it doesn't just show that these efficient two colorings exist. It actually provides a way to construct them using Hamming codes.
Those Hamming codes keep popping up. Remind me how they fit into all of this.
Of course. Hamming codes are a special type of error-correcting code, super efficient at finding and fixing errors in data. But what's cool is their structure is perfect for building these efficient two colorings and, by extension, efficient Boolean functions.
So it's like getting a bonus from those error-correcting properties, right?
Yeah.
We get efficient Boolean function representations, too. How does it actually work? How do Hamming codes shape these colorings?
It's all about how they partition the Hamming graph. A perfect two coloring needs to split the vertices into two groups so that every vertex has the same number of neighbors with the opposite color. Hamming codes let us do this in a way that's perfectly balanced and fits right in with Boolean functions.
So we use the Hamming code as a guide to divide the graph into color regions, which then turn into efficient Boolean function representations.
Exactly, and this has some big implications for how we use Boolean functions. One key thing is the density of ones, which, remember, is how many true outputs the function has.
We talked about how controlling that density is super important in things like cryptography and circuit design, right?
Precisely. For example, in many encryption algorithms, you need Boolean functions with a balanced density of ones and zeros to make sure things are random and hard to predict. Too many of one or the other, and there might be weaknesses that hackers can exploit.
Oh, I see.
Using these efficient two-colorings based on Hamming codes, cryptographers can create Boolean functions with very specific densities, making their encryption much stronger.
So it's like using math to make our digital communication more secure.
Exactly.
What about circuit design? How do these efficient representations help there?
Well, in circuit design, the fewer inputs a Boolean function needs, the simpler, faster, and more energy efficient the circuit can be. Every input means another physical component in the circuit. Fewer inputs, less complex circuit, less power used.
It's like streamlining those logical operations, finding the most elegant way to represent them in the hardware.
Exactly. And the methods we've talked about, especially those using Hamming codes and RM-like codes, give designers powerful tools to do just that. They can find functions with specific properties like a certain density or degree while making sure they use the smallest number of inputs possible.
It's amazing how it all comes together. From these abstract ideas of Hamming graphs and perfect colorings, we're now talking about real-world applications in things like cryptography and circuit design.
It really shows you the power of mathematical thinking, how it can shape the world in concrete ways.
You know, thinking back on this whole deep dive, it really emphasizes that this quest for efficient representation isn't limited to just these applications. It's a problem that comes up everywhere, from computers to biology to economics.
Absolutely. Whether you're trying to compress data, design algorithms, or even just understand complex systems, the key is being able to represent them clearly and concisely.
That's where mathematics shines, giving us the tools and ways of thinking to analyze, understand, and optimize these representations. I think we've done a pretty good job unpacking a ton of information about these perfect colorings.
We've certainly covered a lot of ground.
From those complex details to their surprising uses, this has been quite a journey.
Indeed. But even with everything we've discussed, we're only scratching the surface. There's so much more to explore in this field.
I'm excited for the next deep dive. But for now, thanks so much for sharing your expertise. You've really guided us through this fascinating and complex world of math.
It was my pleasure. And to all our listeners, thank you for joining us on this journey. Hopefully you have a new appreciation for these elegant and useful perfect colorings. Until next time, keep your mathematical minds active, and remember, there's always more to learn, discover, and connect in this vast and beautiful world of knowledge.
Welcome back, everyone, for another deep dive. This time, we're going to be looking at perfect colorings in graph theory.
Oh, very cool.
And specifically, we're going to be kind of focusing on the Hamming graph.
Okay.
So you can think about the Hamming graph as like a visual representation of words and their differences.
Okay.
And this idea of like words being different from one another in certain positions is really important for things like coding theory.
Okay.
So that's kind of the area that we're going to be diving into. And the question that we're really going to be exploring is, can we create these special colorings, these perfect colorings, in a way that is kind of like a perfectly designed machine, like where there's no unnecessary parts?
Oh, okay. I see what you mean. So it's kind of like we're going to be looking at the most efficient way to create these colorings.
Exactly. And we're going to be looking at a paper by Bratzi and Makhnev called "On Perfect Colorings of the Hamming Graph with Essential Arguments."
All right. Sounds pretty dense.
It is. It is. And I'm happy to have you here to kind of walk us through this paper and explain to everyone what all this means.
Yeah, well, I'm excited to try and break it down.
Great. So why don't we start with just making sure that everyone is on the same page with some of the basic definitions here.
Okay, sure.
What exactly is a perfect coloring?
Well, in a very general sense, you have your graph, and you're coloring it in a way that every every vertex or every node, if you want to think about it that way,
Okay.
of a particular color is adjacent to the same number of vertices of all the other colors.
Okay.
So let's say you have a 3 coloring.
Hmm.
Every red vertex
Okay.
is next to, say, 2 blue vertices and 2 green vertices.
Got it.
And so it's like a very structured way to color these graphs.
Yeah, so it's like a meticulously organized neighborhood
Exactly.
where like each house or vertex in this case has like a specific number of neighbors of each different color.
Exactly. And this structure has a lot of really interesting properties that are useful in various areas of mathematics.
Okay, cool. And so the Hamming graph, as we kind of mentioned before, is like a visual representation of words and their differences. How does that work?
Yeah, so each vertex in a Hamming graph corresponds to a word.
Okay.
And let's say the words are of length 3.
No.
2 vertices are adjacent if their corresponding words are different in just one spot.
Oh, okay.
So like cat and hat would be adjacent in the Hamming graph,
Interesting.
but cat and dog would not be.
Okay, so it's like those word puzzles where you like change one letter at a time
Exactly.
to transform one word into another word.
Yes.
Okay.
Yeah.
That's interesting. And so this paper is really focusing on perfect colorings of the Hamming graph
Okay.
that have this unique characteristic of having what they call non-essential arguments.
Oh, okay. So what does that mean exactly? Like an essential argument?
Right.
That sounds kind of complicated.
Yeah, so you can kind of think of it like this. Every position in those words that the vertices represent, matters. So like if you were to change even one of the letters in one of those words, it would like completely change the coloring.
Oh, okay, I see. So it's like there's no redundancy.
Exactly.
Every position has to be exactly the way it is for the coloring to work perfectly.
Exactly. And so the paper really dives into how to construct these efficient perfect colorings.
Right.
And also like explores the relationship between the number of these essential arguments and the structure of the coloring itself.
So it's like trying to find the most efficient way to color the Hamming graph with these perfect coloring.
Right, where everything has to be exactly the way it is for it to work.
Exactly.
Okay. One of the things that they talk about a lot in this paper is this idea of a quotient matrix. Have you ever heard of a quotient matrix?
I'm a little fuzzy on the details.
Okay.
I know it has something to do with defining the rules of the perfect coloring, but maybe you can refresh my memory a bit.
Yeah. So a quotient matrix essentially is it's a matrix that describes the relationship between the colors in a perfect coloring.
Okay.
So like each entry in the quotient matrix will tell you how many neighbors of a certain color
Okay.
a vertex of another color has to have.
Oh, okay. So it's like a blueprint.
Exactly.
For the perfect coloring. You know, like it tells you how many houses of each color should be next to each other in that neighborhood analogy.
Exactly. So for example, like one entry in the quotient matrix might say that every red vertex has to have 2 blue neighbors.
Okay, that makes sense. So the quotient matrix really defines the structure of the perfect coloring.
Precisely. And one of the kind of central questions that this paper is trying to get at is whether the number of these essential arguments in these efficient perfect colorings can grow significantly based on the properties of the coloring.
Okay, so as the perfect coloring becomes more complex, could the number of those essential arguments explode? Right, exactly. Could it like grow exponentially?
Wow, okay. That would be pretty wild.
Yeah.
Like compound interest or something like that.
Yeah.
It just keeps growing and growing.
Exactly. And so to explore this question, the paper dives into some pretty like heavy-duty mathematical concepts.
Okay, like what?
They talk about things like eigenvalues of a graph.
Okay.
And eigenfunctions and degrees of functions. I'm sure some of our listeners out there are familiar with those concepts.
Sure.
But maybe not everyone. So I don't know, maybe you can give us a little bit of a crash course in those ideas.
Yeah, sure. So eigenvalues and eigenfunctions, they're kind of like they help us understand the underlying structure of a graph.
Okay.
So think of an eigenvalue as a special number associated with a matrix.
Okay.
And in this case, it would be like the adjacency matrix of the graph.
Okay.
And an eigenfunction is like a special function that's associated with that matrix and that eigenvalue.
Got it. And they basically reveal kind of hidden patterns in the connectivity of the graph.
Okay, so it's like they're decoding the graph's DNA.
Exactly.
Revealing like its inherent structure, how information flows through it.
Exactly. Yeah, they're very powerful tools. And then the degree of a function is a measure of its complexity.
Okay.
Particularly when we're talking about Boolean functions, which we'll get to later.
Okay.
It refers to the minimum degree of a polynomial that can represent that function.
Got it. So a higher degree means like a more complex function.
Exactly.
Okay, cool.
Yeah.
So the paper kind of connects all of these ideas, these eigenvalues and eigenfunctions and degrees of functions,
Right.
to show that the number of essential arguments in a perfect coloring can actually grow exponentially, depending on the properties of the coloring's quotient matrix and the graph's eigenvalues.
Wow. Okay, so they're really diving deep into the math here. So how do they go about proving this? Like, what's their approach?
Well, they have this kind of clever step-by-step construction process where they build these efficient, perfect colorings
Okay.
using these two key ingredients. The first one is called uniform collections of colorings.
Okay. Uniform collections, what are those?
Yeah. So imagine that you have multiple ways to perfectly color the same graph, but all of them have the same overall like distribution of colors.
Oh, okay, so it's like having different color palettes that all achieve the same visual balance.
Well, exactly.
But use different shades.
Yeah, exactly.
Interesting.
And the paper shows that for every perfect coloring, you can actually generate a uniform collection of colorings.
Oh, okay. So that becomes like a building block
Exactly.
to their construction.
And the other key ingredient is called a partition into RM-like codes.
Okay. Partitions into RM-like codes. I have to admit I'm not really familiar with those either.
Yeah, so RM-like codes are special types of colorings that are really important in coding theory.
Okay.
And basically what they do in this paper is they partition the vertices of the Hamming graph into these special codes.
Okay, so it's like dividing the graph into different zones.
Exactly.
Each with unique characteristics.
Right. And they use the properties of these codes to then create ever larger perfect colorings that still have the desired properties, like no non-essential arguments.
Okay, that's fascinating. So they're kind of like building up these perfect colorings piece by piece.
Exactly. And along the way, they introduce these concepts of density of coloring and density vectors.
Density, okay. What exactly does density refer to in this context?
So density essentially measures like how often each color appears in the coloring.
Oh, okay, I see. So it's like the proportion of vertices assigned to a specific color.
Exactly.
Like a color census for the graph.
Yes, exactly. And the density vector is just a list of those densities for all the colors.
Okay, so it gives you a snapshot of the overall color distribution.
Right. And what's really cool is that the paper shows that for a perfect coloring, you can actually figure out the density vector just by looking at the quotient matrix.
Oh, wow, that's interesting. So there's a direct connection between the rules of the coloring and the overall color distribution.
Exactly. And this connection becomes really important when they're analyzing the colorings that they're constructing to make sure that they actually have the properties that they want them to have.
Okay, that makes sense. So they're kind of like checking their work, making sure everything lines up.
Right, exactly.
Now, one of the really intriguing parts of this paper is where they kind of shift gears a little bit and start talking about Boolean functions.
Okay. Yeah, I remember we touched on that a little bit earlier, but maybe you can remind us, what exactly are Boolean functions and how do they connect to these perfect colorings?
Right, so Boolean functions are basically functions that take binary inputs, like zeros and ones, and they spit out a binary output, either a 0 or a 1.
Okay, and they're like the fundamental building blocks of digital circuits and computers, right?
Exactly. They're like the tiny switches that control the flow of information. Now, what's really fascinating is that certain types of Boolean functions can actually be represented as perfect colorings of the Hamming graph.
Okay, that's a pretty wild connection.
Yeah.
How does that work? Like, how do you go from a function to a coloring?
Okay, so let's imagine a Boolean function with, say, 3 input variables. Each of those variables can be a 0 or a 1, so you have a total of 2 to the 3, which is 8 possible combinations of inputs.
Okay.
Now, the Hamming graph for words of length 3 also has 8 vertices, right?
Right.
So each vertex in that Hamming graph can represent one of those input combinations for the Boolean function.
Got it.
Now, we color each vertex based on the output of the function for that specific input combination. So if the function outputs a 1 for a particular input, we color that vertex, say, black. And if it outputs a 0, we color it white.
So you end up with a black and white coloring of the Hamming graph that represents the Boolean function.
Exactly. And now we can use all the tools and insights of graph theory to analyze and manipulate these functions.
That's pretty amazing. So it's like you're translating a complex logical circuit into a visually intuitive map where the colors represent the flow of information.
Exactly. And this connection is particularly valuable when we start talking about special types of Boolean functions that are really important in cryptography. Things like correlation immune functions and resilient functions.
Right. These are those functions that are really good at like hiding information and resisting tampering.
Right, exactly. They're like the guardians of secure communication.
And the paper shows that these resilient functions actually correspond to perfect colorings of the Hamming graph with specific properties.
Right. And one of the key properties is balance. So a perfectly balanced coloring, where the two colors representing the output values of 0 and 1 are distributed as evenly as possible across the vertices. That corresponds to a highly resilient Boolean function.
Oh, okay, I see. So the more balanced the coloring, the harder it is for an attacker to like manipulate the function's inputs to get a desired output.
Exactly. Because any small changes to the inputs are likely to lead to unpredictable changes in the output.
Got it. So it's like adding a layer of randomness or uncertainty.
Exactly. It's like a shield that masks the function's behavior.
So does achieving this perfect balance always come at a cost? Like, are there any trade-offs involved?
Well, yeah, sometimes perfectly balanced functions might be more complex.
Okay.
They might require a higher degree, which could make them more computationally expensive.
So there's like a balancing act between maximizing resilience and minimizing complexity.
Exactly. And that's what's so cool about this paper. It actually provides methods to construct colorings that strike that balance.
That's impressive. But the paper doesn't stop at simply connecting colorings and Boolean functions, right? It also brings in the concept of degrees of functions.
Oh, absolutely. Remember, we talked about degree earlier. It's essentially a measure of how intricate a Boolean function is.
Right, like a rating system for Boolean functions.
Exactly. And this paper cleverly links that degree to the structure of the corresponding perfect coloring of the Hamming graph.
Okay, this is where it starts to get really interesting. How does the coloring reflect the function's degree? Like, what's the connection there?
Well, it turns out that the degree of the function is closely related to the properties of the eigenfunctions that are associated with the coloring.
Okay.
Remember, those eigenfunctions, they kind of reveal the hidden patterns and structure within the graph.
Right, they're like the whispers of the graph telling us its secrets.
Exactly. So by analyzing those eigenfunctions, we can actually determine the degree of the Boolean function that's represented by that coloring.
Can you give me an example?
Yeah, sure.
Yeah.
So let's say we have that quotient matrix we talked about earlier.
Right.
8, 3, 5, 6.
Okay.
Remember, this represents a perfect 2 coloring of the Hamming graph of size 11. Now, using the techniques in this paper, we can analyze the eigenfunctions associated with this coloring and determine that the corresponding Boolean function actually has a degree of 3.
Oh, wow, that's cool. So you can just like look at the coloring, analyze its eigenfunctions, and bam, the degree of the function it represents.
Exactly. And knowing the degree is crucial, especially in cryptography, because functions with higher degrees are generally more resistant to certain types of attacks.
So a higher degree means a more secure function.
Exactly. And that's why this connection between the coloring and the degree is so powerful.
It's like the coloring is giving us a visual clue about how secure the function is.
Precisely. And the paper really emphasizes this deep connection between these mathematical concepts and their real-world applications.
This is really fascinating stuff. So we've talked about how these colorings can represent Boolean functions.
Right.
And how the structure of the coloring can tell us things about the function's complexity and resilience.
Yeah.
But the paper doesn't stop there, right? It goes even deeper into this realm of correlation immune Boolean functions.
Oh, absolutely. And this is where the connection to cryptography becomes even more apparent.
Okay, can you remind us what correlation immune Boolean functions are again?
So these are a special type of Boolean function where the output is statistically independent of any subset of its input variables up to a certain size.
Okay, and that's really important for security, right?
Exactly, because it means that even if an attacker knows the values of some of the inputs, they still can't predict or deduce anything about the output.
So it's like a master of disguise, even when partially exposed.
Precisely. And that makes them incredibly valuable for designing secure cryptographic systems.
Okay, so how does the paper connect these correlation immune functions to the perfect colorings?
It shows that the order of correlation immunity, which basically tells you how many input variables the function can be independent of,
Right.
is directly related to the structure of the corresponding perfect coloring of the Hamming graph.
Oh, wow. So the more correlation immune the function is, the more structured the coloring has to be.
Exactly. And the higher the order of correlation immunity, the more balanced and organized the quotient matrix needs to be.
So it's like the coloring itself reflects the robustness and resistance of the function.
Precisely. And this connection is really valuable because it gives us insights into how to design and analyze these special types of Boolean functions.
That's amazing. We're using these visually intuitive colorings as a tool to understand these complex functions that are so crucial for security.
Exactly. And it's all thanks to the power of graph theory.
Okay, so we've talked a lot about the connection between colorings and Boolean functions and all these amazing properties. But let's shift gears a little bit and talk about the actual construction process that the paper presents for these efficient, perfect colorings.
Okay, sure.
Remember those two key ingredients, uniform collections and partitions into RM-like codes.
Yeah.
Can you walk us through how they actually combine those to create these remarkable colorings?
Yeah, absolutely. So the first step is to start with a uniform collection of perfect colorings of a smaller Hamming graph. These are like our building blocks.
Okay.
And then we partition the vertices of a larger Hamming graph into those special RM-like codes.
Right, like dividing the construction site into different zones.
Exactly. And the magic happens in the third step, where we use the uniform collection to color the vertices within each of those RM-like codes.
So we're taking those prefabricated modules and assembling them according to a specific blueprint.
Precisely. And the way these smaller colorings are combined is really clever. The paper gives a specific method for interlacing them to make sure that the resultant coloring of the larger Hamming graph is also a perfect coloring.
So it's like weaving together different threads of color to create a larger tapestry.
Exactly. And the result is a perfect coloring that's not only visually stunning, but also incredibly efficient.
Because it has no non-essential arguments.
Exactly. Every single position in those words represented by the vertices matters.
Okay, so how do they actually prove that these colorings are so efficient?
Well, the proof relies heavily on the properties of the uniform collections and the RM-like codes. They basically show that if you try to remove any argument from the coloring, it's going to mess everything up. It won't be a perfect coloring anymore.
Oh, I see. So it's like a perfectly balanced ecosystem. Everything has its place, and if you remove something, it throws off the whole system.
Exactly. But the paper goes even further. It also explores how the number of essential arguments in these colorings relates to the structure of the coloring itself.
Okay, and what did they find?
They found that the number of essential arguments can actually grow exponentially based on certain properties of the coloring, particularly those captured in the quotient matrix.
Wow, exponential growth. That's pretty impressive.
Yeah, it is. And they actually establish a precise mathematical relationship between those off-diagonal elements of the quotient matrix and the number of essential arguments.
So even small changes in those elements can lead to big gains in efficiency.
Exactly. It's like a ripple effect.
This is all really mind-blowing stuff. We've explored so much, from the connection between colorings and Boolean functions to the role of degree and the importance of correlation immunity. And we've even delved into the construction process for these amazing, efficient, perfect colorings.
I know, it's a lot to take in, but it's also interconnected and fascinating.
It really highlights the power of mathematics to not only uncover these hidden connections between different concepts, but also to solve real-world problems.
Absolutely. And that's what makes this research so exciting.
I think we've covered a lot of ground for now. Maybe we should take a short break to let our listeners absorb all of this information and then come back to wrap things up.
Welcome back, everyone. It's amazing how much ground we covered in our exploration of perfect colorings.
I know, right? It's a testament to how rich and interconnected these mathematical concepts are.
So before we wrap up, maybe we can just highlight some of the key takeaways for our listeners. Sure. I think the biggest takeaway is that these perfect colorings of the Hamming graph, these really abstract mathematical objects, have a profound impact on real-world applications.
Right, like in coding theory and cryptography.
Exactly. And the paper we discussed shows how we can construct these colorings in a really efficient way, ensuring that every part of the coloring is essential. no wasted space.
Yeah, it's like building a machine with absolutely no unnecessary parts.
Precisely. And the paper provides this clever construction method using those uniform collections and partitions into RM-like codes.
Right, those were like our building blocks. And the way they're combined is so ingenious.
Yeah, it's like a perfectly choreographed dance. And what's amazing is that the number of essential arguments in these colorings can actually grow exponentially based on certain properties of the coloring itself.
That exponential growth is just mind-blowing. It means that even small changes in the structure of the coloring can lead to huge gains in efficiency.
Absolutely. And then there's this fascinating connection between these perfect colorings and Boolean functions, those fundamental building blocks of digital circuits.
Yeah, that connection was a real eye-opener for me. It's like we're using these visual colorings to understand these complex logical functions that are so crucial for security.
Exactly. And the paper shows how we can use this connection to design highly resilient Boolean functions that are really good at resisting tampering and hiding information.
It's like we're harnessing the power of graph theory to create these unbreakable codes and ciphers.
Precisely. So, in a nutshell, this paper highlights the incredible power and elegance of mathematics. It shows us how seemingly abstract concepts like perfect colorings can have a profound impact on our world, especially in the realm of information security.
This deep dive has really been a journey of discovery, uncovering hidden connections, and revealing the beauty and power of these mathematical ideas. I think we've given our listeners a lot to think about.
I agree. Hopefully, this has sparked some curiosity and inspired further exploration. Who knows what other amazing connections and applications are out there waiting to be discovered?
That's the beauty of mathematics. There's always more to learn and explore. Well, that's it for this deep dive. Thanks for joining us. We hope you'll tune in again next time for another exciting journey into the world of knowledge and discovery. Welcome back, everyone. We're diving into a paper today that's, well, colorful. It's all about perfect colorings in Hamming graphs.
That's right. We're going to get pretty deep into the math here, but I think it'll be worth it. There are some really elegant ideas in this paper.
Okay, so for those who might not be familiar, what exactly is a perfect coloring in this context?
Imagine a graph, our Hamming graph, right? The vertices are words, and two words are connected if they only differ by one letter. A perfect coloring, then, is a way to color these vertices. So each vertex of a given color has a fixed number of neighbors of each other color. It's like creating this balanced distribution of colors across the whole graph.
So if like one red vertex has 3 blue neighbors and 2 green neighbors, then every red vertex will have that same setup.
Exactly. It's all about that balance and symmetry. And the way we keep track of all this, the rules of this coloring game, if you will, is with a quotient matrix.
The quotient matrix. So that tells us how many neighbors of each color each vertex has.
Precisely. Like, if the entry in row 2, column 3 is 5, that means every vertex of color 2 has 5 neighbors of color 3.
Okay, got it. But we're not just looking at any old perfect coloring here, right? We're specifically interested in those without, what did the paper call them? Useless colors.
Right. We want to make sure every color is essential. We don't want any redundancy, any colors we could just take out without changing the overall structure.
Sort of like the idea of essential and non-essential arguments and functions. You can't get rid of the essential ones without messing things up.
Exactly that. It's about finding the most efficient, elegant way to color these graphs. No wasted colors. Now, the paper does get into some fairly advanced math to do all this. We're talking eigenvalues, eigenvectors, even finite fields.
Yeah, our listeners are pretty sharp, but maybe a quick recap on those couldn't hurt, just to make sure everyone's on the same page.
Sure. Eigenvalues and eigenvectors, they're fundamental tools in linear algebra, right? They help us understand how linear transformations behave, and they're crucial for analyzing the structure of graphs, especially here.
In finite fields, they're a bit more abstract, aren't they? Why do we need those?
Well, finite fields, they're kind of like the familiar real numbers, but with only a finite number of elements. They have these really neat properties that make them super useful in coding theory, especially for building error-correcting codes.
And those codes somehow tie back into these perfect colorings.
They do. We'll get to that later. But just to solidify things, maybe we should go over the formal definition of a perfect coloring as it's given in the paper. It might clarify some things.
Yeah, good idea. Lay it on us. What's the official definition?
So formally, a perfect coloring is defined like this. We've got a graph G, right, with vertices V. We have K colors, which we call K. A perfect coloring is a function from V to K. And here's the key. For each vertex V with color I, it has exactly subi J sub neighbors of color J. And all these relationships are captured in this KXK matrix, the quotient matrix, which we denote as subi J sub.
So that quotient matrix really is the blueprint for the whole coloring scheme, huh? It tells us exactly how to distribute those colors. Now, I know the paper poses two fundamental questions about these colorings. What are those, again?
So the first question is all about, well, given a specific quotient matrix, what's the smallest Hamming graph that we can actually perfectly color with it? It's a question of existence, you know? Can we always find a Hamming graph that fits the pattern, and how small can we make it?
So it's about finding the most compact canvas for our coloring, in a way. What of the second question?
The second one kind of flips it around. It says, okay, assuming we can find a perfect coloring for a given matrix, what's the largest Hamming graph we can color without needing any non-essential arguments or colors? It's about scalability and efficiency, seeing how far we can push things while keeping that perfect balance.
Right. So first we find the smallest canvas, then we see how big we can make the artwork without wasting any paint. And this paper is tackling that second question specifically. Yeah.
Exactly. They want to show that under certain conditions, the size of the colorable Hamming graph can actually grow exponentially with the complexity of the coloring. And that complexity is essentially measured by the off-diagonal elements of the quotient matrix.
Okay, so more complex coloring, potentially a much, much larger graph. That's pretty cool. But before we get into the details of how they actually do that, there's this whole concept of uniform collections that seems pretty important. What are those exactly?
Oh, yeah. Uniform collections. They're key to the whole construction. Think of it as a set of perfect colorings, all based on the same quotient matrix. And the special thing about them is, no matter what vertex you pick in the graph, the combination of colors you see around it is always the same, no matter which coloring from the collection you're looking at.
So it's like having multiple versions of our perfectly colored neighborhood, all with the same rules, but maybe different arrangements of the houses.
A perfect analogy. And what makes them so important is how they're connected to the very existence and properties of perfect colorings. Lemmas 2 and 3 in the paper lay all that out.
Okay, and what do those lemmas say exactly? I know we're getting into the weeds here, but I think it's worth it.
Sure. So Lemma 2 says that within a uniform collection, each color appears with a frequency that's, well, directly proportional to its density in any of the individual colorings. Like if 20% of the vertices in one coloring are blue, then 20% in every coloring in that collection will be blue. Keeps everything consistent.
So still all about that balance, huh? What about lemma 3? What does that tell us?
Lemma 3 shows that these uniform collections aren't some weird special case, actually. You can build one from any perfect coloring. You just shift the pattern around. It's like taking our perfectly colored neighborhood and making copies of it, sliding them around so they overlap in different ways. And each of those overlapping patterns is still a perfect coloring.
Huh, interesting. So you can generate a whole family of these perfect colorings from just one. But there's one more piece of the puzzle before we get into the actual construction. The paper talks about these RM-like codes. What are those and why are they important?
RM-like codes, those are really where things get interesting. They're kind of this bridge between coding theory and graph theory, inspired by these error-correcting codes, Reed-Muller codes, really important in communications to, make sure data doesn't get corrupted. And here in our Hamming graph world, they give us a way to, partition the vertices into these groups with special properties.
So instead of just individual vertices words, we're grouping them into these code word districts. What's the advantage of that?
That's the clever bit. Lemma 4 in the paper, it shows that there's this special type of perfect coloring that uses these RM-like codes. It's like dividing the graph into these districts, and each one gets a color. And because of the way RM codes work, we can get these perfect colorings with no wasted colors, nothing extra.
Okay, hold on. Back up a second. How do error-correcting codes, translate into perfect colorings? How does that get rid of those useless colors?
Think about it this way. You've got a word, right? It's a vertex in our graph. You want to send it, but there's noise, errors, some letters might get flipped. RM codes, they add in some redundancy so you can detect and fix those errors. Now, each district, each code word, it's a bunch of vertices that are close together, meaning they only differ by a few letters.
So words that are easy to mix up if there's an error. Okay, but how does that help with the coloring?
The key is, within each district, we can assign colors in a balanced way. Each vertex has the right number of neighbors of each color. And because it's all based on these error-correcting codes, the whole coloring is not just perfect, it's efficient. No extra colors hanging around because each one has a specific job to do, keeping the balance within its district and across the graph.
Ah, I see. So the codes are like, they're the guidelines for placing the colors, but they also make sure everything lines up right at the edges.
Exactly. It all fits together perfectly. But there's a catch, of course. Finding these RM-like codes isn't always easy. It depends on the Hamming graph itself, its size, and the alphabet we're using for our words.
Right. So it's not just pick a graph, any graph, and bam, there's your code. There's this whole deeper connection between the structure of the graph and whether these codes even exist.
Precisely. It's what makes this whole area so fascinating, really. You got graph theory, coding theory, even abstract algebra all mixed together.
So we've got our perfect colorings, our uniform collections, and now these RM-like codes that are like the secret sauce for making everything work. I'm ready to see how it all comes together in the actual construction the paper lays out.
All right, let's do it. Theorem 1, that's where the magic happens. It's the blueprint for building these large, efficient colorings. A few steps involved, but we've got all the pieces now.
Lead the way.
Yeah.
I'm eager to see how this masterpiece unfolds.
Okay, so imagine we've got a bunch of small, perfect colorings, each on a, relatively small Hamming graph. They form a uniform collection, so they've all got that balance we talked about. Think of them as our building blocks.
Like perfectly crafted tiles, each with its own pattern, but designed to fit together.
Perfect analogy. Now, Theorem 1 tells us how to combine those small colorings to make a bigger coloring on a much, much larger graph. And the key is, we use those RM-like codes to guide the process.
So we're arranging the tiles according to a pattern from the codes. But how do we know the colors will match up at the edges? That seems tricky.
That's where the beauty of the RM-like codes comes in. The way they're structured, their distance properties, they ensure those colors align perfectly. Remember, vertices in the same district, they're close together. So when we piece the colorings together according to the code, those color transitions are smooth, the balance, the symmetry, it all stays intact.
So the codes are not just placing the tiles. They're making sure the colors blend together seamlessly. Pretty neat.
It is. And the best part, this construction, it doesn't just give us any old perfect coloring. It guarantees there are no non-essential arguments, no wasted colors. Every single color has a job to do.
We're not just going bigger, we're going bigger and more efficient. Every color matters. That's amazing.
Right. And it gets even better. Corollary 2, it takes this whole thing a step further. It says we can repeat this process. Take the larger coloring we just made and use that as a building block to make an even bigger one.
Whoa. So we can keep scaling up, building this whole hierarchy of perfectly colored graphs, each one based on the one before it. But is there a limit? Can we just keep going forever?
That's the question, isn't it? Corollary 2 says we can keep going, but there are some, subtle mathematical constraints. Things get a bit tricky with the quotient matrix and those RM-like codes. But the paper shows that in a lot of cases, the size of the graph we can color, it can grow exponentially as we repeat this process.
Exponential growth. That's a powerful concept. It means as the coloring gets more complex, the size of the graph can just explode. But why is that such a big deal? What are the implications of that kind of growth?
It is a big deal. Exponential growth in, math, computer science, it's often a sign that you found something really efficient. You can get huge results with relatively little effort. Here, it means we can make these super complex, perfectly balanced colorings on these massive graphs without, needing a ton of resources.
Okay, I'm starting to see why that's exciting. It's like finding a shortcut, a way to do something really hard but make it surprisingly easy. But can you give me an example of where this efficiency would actually matter?
Sure. Think about Boolean functions, right? They're basically just colorings with two colors, 0 and 1.
Yep.
And they're like the foundation of all digital logic. Everything from the circuits in our phones to the algorithms running AI, it's all built on Boolean functions.
Right, so back to our neighborhood, it's like now each house can be on or off.
Exactly. Now imagine you're building a circuit, right? But it's super complex, tons of inputs, maybe millions. Each input is a variable in a Boolean function, and the output of that function, that's what the circuit does. And the more complex that function is, the more intricate, more energy hungry the circuit becomes.
So a more complicated function means a less efficient circuit. Got it.
Yeah.
So where do our colorings fit in?
Well, Theorem 2 and Corollary 3 in the paper, they show that using this construction we've been talking about, the one with the perfect colorings and the RM-like codes, we can make Boolean functions with a ton of essential variables, and that number grows exponentially with the complexity of the function.
Essential variables, remind me what those are again. They're like the important inputs, right? The ones that actually matter for the function's output.
You got it. Changing an essential variable changes the result. Changing a non-essential one, nothing happens. So these theorems are saying we can build functions that are sensitive to a huge number of inputs, but without them becoming super complicated structurally.
So we can have our cake and eat it too, kinda. We get these powerful, sensitive functions without them becoming unwieldy and inefficient.
Exactly. And that's a big deal for circuit design. It means potentially building circuits that can process tons of information without needing tons of power or becoming ridiculously huge.
That's pretty mind-blowing. We're talking like revolutionizing computers and electronics here. But are there any other areas where this stuff might have an impact?
Oh, definitely. The coding theory connection is probably the most obvious one. Those RM-like codes, right? They're essential for building these colorings. But the fact that they work so well here, it suggests there's this like deep connection between coding theory and these perfect colorings. More research here could lead to totally implications for everything: telecommunications, data storage, you name it.
So faster internet, more reliable wireless, even safer ways to keep our data, all thanks to some, abstract math about coloring graphs. It's pretty amazing how these things connect.
It is. It's like math. It often starts as this like pure pursuit of understanding, but then it ends up giving us these incredibly powerful tools that can change the world.
Speaking of pursuits, I feel like we've just scratched the surface here. Are there any, big unanswered questions or areas you think are ripe for more exploration, something our listeners can ponder as they, go on their own mathematical adventures?
One thing that comes to mind is what are the limits of this exponential growth? Can we really just keep scaling up these colorings forever? Or are there fundamental boundaries we hit because of the way Hamming graphs work or those RM-like codes? Figuring that out could lead to even deeper insights into, the structure of these objects and how we can use them.
Yeah, it's like we've discovered this new continent, but there's still so much left to explore, so much we don't know.
Exactly. And then there's the whole challenge of actually applying these ideas in the real world. Can we use these efficient colorings to make better algorithms, design more reliable communication systems, maybe even totally new ways of computing? There's so much potential here.
This has been a wild ride, for sure. I'm betting our listeners are buzzing with excitement right now. This paper really highlights the power and beauty of math and how it can lead us to these unexpected places. Before we go, I want to encourage everyone to, check out the paper itself, dive in and explore this world of graph theory and coding theory. It's a fascinating journey.
Couldn't agree more. There's so much more to learn, and who knows what amazing discoveries are waiting out there for those who are willing to, dig in and explore.
And with that, we'll wrap up this deep dive. Thanks for joining us, everyone. Until next time, keep exploring, keep questioning, and keep that love of knowledge alive. Welcome back, everyone, to another deep dive. This time, we're going to be tackling some pretty fascinating math. We're going to be looking at Denis Krotov's recent work on perfect colorings of Hamming graphs.
Yeah, definitely a lot to unpack there.
It is. It is. But, as always, we're going to try to make it approachable and fun. But before we even get into the fun stuff, I always like to, set the stage a little bit. Yeah. So for our listeners, can you give us a quick recap of what we're dealing with here? What are Hamming graphs? And what do we mean by a perfect coloring in this context?
Sure. So Hamming graphs, you can think about them as spaces where each point represents a word of length n over some alphabet of size q.
Got it.
So these words, could be strings of letters or binary code sequences, whatever you want. And then two words are considered adjacent if they differ in only one position.
Okay.
So cat and CO
Got it.
would be adjacent.
So it's the network of these words all connected based on this one position difference.
Exactly. Yeah.
Okay. And then what about this perfect coloring idea?
Right. So a perfect coloring is you assign Hay colors to these words or vertices. And in this coloring, each vertex of color has a fixed number of neighbors of color J.
Okay.
So it's not just random.
Got it.
There's a specific pattern. And this pattern is actually captured by something called a quotient matrix, which basically describes the desired interactions between the colors.
Okay. So it's not just randomly assigning colors. There's a specific structure based on this matrix.
Yeah, exactly. You've got it.
Okay. And what Krotov does is he focuses on this idea of essential arguments, right? Can you break that down for us a little bit? What does it mean for an argument to be essential in this context?
Sure. So in this context, an argument refers to a position within a word. So if you have a word of length 5, each of those 5 positions is an argument.
Got it.
Now, an argument is considered essential if changing the symbol in that position actually changes the color of the word under our perfect coloring.
So basically, if it's non-essential, I could like swap out the symbol in that spot and it wouldn't mess with the coloring.
Exactly. Yeah. So you can think of it as like a way to simplify things, right? You don't really need that argument to achieve the perfect coloring.
Got it. And so what Krotov is doing in this paper is he's trying to come up with a way to create these perfect colorings, but where every argument is essential.
Exactly. Even when you increase the complexity with lots of colors and intricate relationships between them.
Wow. Okay. That already sounds like a pretty significant achievement. Before we dive into the specifics of his construction, though, I think it's important to unpack some of the foundational concepts that he relies on in his work. Things like eigenvalues, degrees of functions, density, and these things called uniform collections. Can we take a few minutes to break those down for our listeners just to make sure we're all on the same page?
Sure.
So let's start with eigenvalues and degrees. I know they're kind of intertwined concepts, but can you explain how they relate to each other and why they're important in this context?
Okay. So eigenvalues are numerical values associated with a graph that give you insights into its structure.
Okay.
So you can imagine you have a function that operates on this graph, right? It assigns values to each vertex, and the degree of this function is connected to the largest eigenvalue. That pops up when you analyze how the function behaves across the graph.
Okay, so the eigenvalue is like a gauge for the complexity of a function on that particular graph.
Yeah, you got it.
Higher degree, more complex function.
Exactly. And this connects nicely to the world of Boolean functions and density.
Okay.
So remember, Boolean functions are basically logical operations that take binary inputs, zeros and ones, and spit out a binary output.
Like the building blocks of digital circuits.
Exactly. And the density of a Boolean function refers to the proportion of outputs that are ones.
So a dense Boolean function would have lots of ones in its output.
Exactly.
Got it.
And what's fascinating is you can represent Boolean functions on these Hamming graphs. And their properties, like density, are deeply intertwined with those eigenvalues and degrees we were just discussing.
Wow. So we're starting to see those connections already. Okay, what about those uniform collections? What are they and how do they fit into Krotov's construction?
So uniform collections, you can think about it as like you have a bunch of perfect colorings of a Hamming graph, and they all have the same quotient matrix.
Okay.
A uniform collection is a special set of these colorings, where if you look at the colors assigned to any particular word, you'll see the same multi-set of colors no matter what word you pick.
Oh, interesting. So each word is getting the same palette of colors from these different perfect colorings, even if the specific arrangement of colors might differ.
Exactly.
Okay. And Krotov uses these uniform collections as the foundation for his construction.
Right.
Okay. And he combines them with another type of perfect coloring, these RM-like codes, to create these new perfect colorings on larger Hamming graphs. Okay, now you're just throwing jargon at me.
Yeah.
What are RM-like codes?
They're not as complicated as they sound.
Okay.
Really, it's a special type of perfect coloring with a very particular quotient matrix.
Okay.
And this matrix has a pattern where the entries are 0 if the row and column indices are congruent modulo Q and 1 otherwise.
All right. I'll take your word for it on that one. But I'm starting to see how these pieces might fit together. So we have these uniform collections, these RM-like codes, and somehow Krotov is combining them to create these new, amazing, perfect colorings with all arguments essential. But how does he actually do that? Can you walk us through the steps of his construction?
Okay, so you can picture, like you start with, a uniform collection of perfect colorings of a smaller Hamming graph.
Okay.
And then you have an RM-like code, which itself is a perfect coloring of another Hamming graph.
Got it.
Yeah.
So we have our two sets of colorings, like different paint palettes.
Yeah, exactly. And then what you do is you combine these to create this brand new, much larger, perfect coloring. And this new coloring, amazingly, has no non-essential arguments.
So it's like mixing those paint palettes in a very specific way to create this brand new palette where every single color matters.
That's a great way to put it.
Okay.
And what's really remarkable is that as you repeat this process, The number of essential arguments doesn't just increase like linearly, it actually grows exponentially.
Wait, exponentially. So it's not just adding a few more each time. It's like multiplying.
Exactly. That's the power of his construction. You can build these incredibly complex colorings where every single position in a word is absolutely critical.
Okay. This is already blowing my mind, but I think I need to see it in action to really grasp it. Can we walk through an example of how this construction actually plays out?
Sure.
Like step by step.
Yeah. So let's start with Theorem 1, where he lays out the actual construction in detail.
Okay.
So what he does is he takes the initial imperfect colorings and he expands them into QM new perfect colorings.
Oh.
And he does this by introducing extra inessential arguments to each of the original colorings. So these new colorings are like copies of the originals,
right,
but with some added baggage.
Like those placeholders.
Exactly, yeah.
They seem useless now, but I bet they become important later.
Exactly, they're part of the bigger picture.
Okay.
And then, here's the really clever part. He defines a new function, f.
Okay.
That takes in all the arguments from both the expanded colorings and the RM-like code, and it uses the RM-like code to stitch together these QM colorings.
So this F is going to be our final, super complex, perfect coloring.
Exactly. So it's like an intricate weaving process, right? And the RM-like code acts as a guide to choose which of the expanded colorings to apply at each point on the larger Hamming graph.
Okay. That sounds incredibly complicated.
It is. But those extra arguments we added, they are crucial.
They're the key to making the whole thing work.
Exactly.
Okay.
And so the way he defines this new function f is by splitting the input into two parts.
Okay.
The first part determines which of the QM colorings to use. And then the second part, combined with the chosen coloring, determines the final color.
Oh, wow. So it's like a nested coloring scheme.
Exactly.
But how do we know that this F actually produces a perfect coloring? And how do we know all the arguments are actually essential?
Okay. So to prove that it's a perfect coloring, what you do is you go through for every point in the new Hamming graph, and you show that the number of neighbors of each color is exactly what the quotient matrix dictates.
Okay, so it's like a giant jigsaw puzzle where every piece has to fit perfectly for the overall picture to emerge.
Exactly.
Okay, and he does that by carefully analyzing how the RM-like code links those individual colorings together.
Exactly.
Okay, and then how does he prove that each argument is essential?
Well, he shows that for any given argument, you can always find 2 points in the Hamming graph that differ only in that argument, but end up with different colors under this new F coloring.
So it's like saying, hey, look, if I change just this one bit, the whole color changes. So it must be essential.
Exactly. It's a very elegant way to prove it.
It is. It is. Okay, so we've got this F function. It creates this perfect coloring. All the arguments are essential. But what about the quotient matrix for this new coloring? How does it relate to the quotient matrices of those original colorings and the RM-like code?
So the quotient matrix for the final coloring, let's call it Q, is actually derived from the quotient matrices of the original colorings, S, and the RM-like code, T.
Okay.
And the exact relationship is a little bit technical.
Okay.
But essentially, Q inherits the structure of S and T.
Got it. So it's like the blueprints for those smaller colorings are woven together to create this master plan for the larger coloring.
Precisely. And what's really cool is that this process can be repeated.
Oh, wow.
Iteratively.
So you can just keep building larger and larger colorings.
Exactly. You can construct perfect colorings of increasingly larger Hamming graphs.
Yeah.
And they all have this essential argument property.
Okay. This is amazing. So we can create these incredibly complex, highly structured colorings where every single bit of information matters. But this all sounds very abstract. What are the practical implications of this? Like, why should we care about these perfect colorings with essential argument?
Well, that's what we're going to get into next. There are actually some really interesting applications of this work in areas like coding theory, cryptography, and even machine learning.
Okay, I'm intrigued. Let's take a break and then dive into those applications.
Okay, so let's really get into the nitty-gritty here. Let's look at the proof of Theorem 1.
Yeah, let's do it.
Where Krotov lays out his construction.
We've talked about the ingredients. We kind of have a picture in mind, but let's see how the sausage is made. Let's see the actual math.
Exactly. So remember, we're working with our uniform collection of M-perfect R colorings of a Hamming graph H or NQ with a quotient matrix S.
Right.
And we have our perfect MQ coloring of HMQ with that special quotient matrix T where the entries are determined by the congruence modulo Q.
Right. Those are our building blocks.
Right. And the first step is to take those initial M colorings and expand them into QM new perfect colorings. And we do that by adding Q1N inessential arguments to each of the original colorings.
Right.
So these new colorings are denoted as DHE plus J, where A ranges from 0 to M1 and J ranges from 0 to Q1.
Right, okay.
And so now what we do is we define this new function F on a larger Hamming graph, HQN plus MQ.
Okay.
And this function is going to be our final complex perfect coloring.
So F is like our master function that takes in all this information and spits out the final coloring.
Exactly.
Okay.
And so how does it work? So F takes in a vertex from this larger Hamming graph, which is basically a tuple of QM plus M elements.
Okay.
And we split that tuple into two parts. The first M elements, which we'll call Y, and the remaining Q elements, which we'll call X.
Got it. So we're splitting the input into a Y section and an X section.
Exactly. And then what we do is we apply our RM-like code, E, to the Y section.
Right.
And that gives us a color because E assigns a color to every vertex in HMQ.
Right.
Right. And then that color basically tells us which of the QM colorings to use on the X section.
Okay, so the RM-like code is like a switchboard. It's telling us which coloring to use based on that Y part.
Exactly. It's like a nested coloring scheme.
Wow. Okay.
Right.
So, but how do we know that this F actually produces a perfect coloring?
Right. So to prove that this function F produces a perfect coloring, we have to go through, and for every vertex in this larger Hamming graph, we have to show that the number of neighbors of each color is exactly what the quotient matrix dictates.
Okay. And how do we do that?
Right. So this involves a lot of careful counting arguments.
Right.
But Krotov meticulously goes through and he shows how using the RM-like code and how it connects these component colorings that everything works out perfectly.
Okay. So it's like a giant accounting problem. We have to make sure everything balances out. Okay. And then once we've shown that it's a perfect coloring, how do we prove that all of the arguments are essential?
Right. So to prove that all the arguments are essential, what we do is we show that for any given argument, you can always find two vertices in this larger Hamming graph.
Okay.
That differ only in that specific argument, but end up with different colors under F.
Okay. So it's like if I tweak just this one little piece, the whole thing changes color. Therefore, it must be important.
Exactly.
It must be essential.
Yeah, it's a very elegant way to prove it.
It is. It is. Okay. So this function F, it takes in all these arguments, creates a perfect coloring. Everything is essential. But what about the quotient matrix for this new coloring? How does it relate to the quotient matrices for those original colorings and the RM-like code?
Right. So the quotient matrix for the final coloring, let's call it Q, it's derived from the quotient matrices of the original colorings S and the RM-like code T.
Okay.
And the exact relationship, again, is a little bit technical. But essentially, you could think about it as Q inherits the structure of S and T in a very specific way.
So the blueprint for the final coloring is somehow combined from the blueprints of the smaller colorings.
Exactly.
Okay, that makes sense.
And what's cool is, again, this process can be repeated.
Oh, wow.
Iteratively.
So you can keep going.
So you can construct perfect colorings of increasingly larger Hamming graphs, all with this essential argument property.
So we're not limited in terms of how big or complex we can make these colorings.
Exactly. And that's really the power of this construction.
Okay. So we've gone through this step-by-step process. We've seen the math. But again, this all feels very abstract. Can we bring it back down to earth a bit? Like, what are the practical implications of this? Why should we care about these perfect colorings with essential arguments?
Right. So one area where this has a lot of potential is in coding theory.
Okay. Coding theory. That's all about error correction, right?
Exactly. So, you know, when you're transmitting information over a noisy channel, you want to make sure that the information arrives at the other end, intact.
Right.
And one way to do that is to use error correcting codes, which essentially introduce redundancy into the data to help detect and correct errors.
So like adding extra bits to the message that can help us figure out if something got messed up along the way?
Exactly. And these error correcting codes, they can be represented as truth tables of Boolean functions.
Okay, I see the connection.
Right. So by manipulating the properties of the Boolean function, we can indirectly manipulate the properties of the code itself.
Got it.
And one of the crucial properties that we can influence is the code's distance.
Distance.
Which is essentially a measure of how well it can detect and correct errors. The higher the distance, the more robust the code.
So a high-distance code means we can handle more errors without losing the original information.
Exactly.
Okay. And how does Krotov's work help us create these high-distance codes?
So Krotov's construction gives us a way to create codes with specific distances, while ensuring that they're as efficient as possible, meaning there's no wasted information.
Wow, that's really cool.
Right, so you're getting more reliable data transmission
Yeah.
with less overhead.
Okay, that makes sense. So coding theory is definitely one big application.
Yeah.
But you also mentioned cryptography, right?
Mm.
How does this tie into the world of secret codes and secure communication?
Right, so in cryptography, you're trying to protect information,
Uh-huh.
right, and make sure that communication is secure.
Right.
And Boolean functions are actually at the heart of many cryptographic algorithms
Okay.
for things like encryption, hashing, and so on.
Okay.
And the security of these algorithms really depends on the properties of the Boolean functions used.
So we need special Boolean functions to make sure our cryptography is strong.
Exactly. And one of the key properties here is nonlinearity,
Nonlinearity.
which basically measures how well a Boolean function resists being approximated by a simple linear function.
Why is that important? Why do we want nonlinear Boolean functions for cryptography?
Because linear functions are easy to analyze,
Okay.
right? They're predictable. So if your cryptographic system is using a linear Boolean function, it's going to be very vulnerable to attacks.
Okay, that makes sense.
But if you use a highly nonlinear Boolean function, you're creating this complex, unpredictable relationship between the input and output.
So the more nonlinear the function, the harder it is to break the code.
Exactly.
Okay, got it. And so how does Krotov's work help us create these highly nonlinear Boolean functions?
Well, his construction allows us to create highly nonlinear Boolean functions with very specific properties, like being balanced or unbalanced, depending on what we need for the cryptographic application.
Okay, so we can basically tailor-make these Boolean functions to fit our specific security needs.
Exactly.
That's really cool.
And because his method ensures that these functions have no non-essential arguments, they're as efficient as possible, which is also really important.
Right, because we don't want our cryptographic systems to be slow and clunky. Okay, this is really impressive stuff. But before we wrap up, you mentioned that there are even applications in machine learning. Can you tell us a little bit more about that?
Sure. So in machine learning, you're basically training algorithms to recognize patterns
Uh-huh.
and make predictions based on data.
Right, so like those algorithms that can tell you what movie to watch next or what product you might like?
Exactly. And one of the key challenges in machine learning is feature selection,
Feature selection.
which basically means identifying the most relevant variables or features that contribute to making accurate predictions.
Okay, so it's like figuring out which pieces of information are actually important for making good predictions.
Exactly.
Okay, that makes sense.
And you can think of these features as like the arguments of a Boolean function,
Okay.
where the output of the function is the prediction made by the algorithm.
Okay, I see where this is going.
Right. So if we use Krotov's construction to create Boolean functions with no non-essential arguments, we're basically ensuring that our machine learning model is only focusing on the most relevant features.
Got it. So it's like we're helping the algorithm to cut through the noise and focus on what really matters.
Exactly.
Okay, and what are the benefits of that?
Well, first of all, it leads to more efficient models
Okay,
that require less computational power, less memory.
so they're faster and they use less resources.
Exactly.
Okay, that's important.
Second, by removing those irrelevant features, you actually reduce noise
Okay.
and improve the accuracy of the model's predictions.
So like making the algorithm smarter, it's helping it to make better decisions.
Exactly.
Wow.
And then finally, using only essential features
Hmm.
makes the model more interpretable,
Interpretable.
which means we can understand how it's making its decisions,
Okay.
which is really important in sensitive applications like healthcare or finance.
Right, because we need to be able to trust these algorithms. We need to understand how they're working.
Exactly.
Wow. Okay, so this is really incredible stuff. We've gone from these abstract mathematical concepts to real-world applications in coding theory, cryptography, and machine learning. It's amazing how this all ties together.
It is. It's a great example of how even in pure mathematics, there's often practical value waiting to be discovered.
Absolutely. All right, so we've spent quite a bit of time with Krotov's construction. We've seen the building blocks, we've seen the proof, but I think now it's time to really see the bigger picture here. How does this work? How does this all actually play out in the real world? What are the implications?
Right. So one area where this has huge potential is in coding theory.
Okay, coding theory. So that's all about transmitting information reliably.
Exactly. When you're sending information over a channel that might be noisy, like think about sending signals to a spacecraft or storing data on a hard drive.
Right. We need to make sure that the information gets there intact, even if there are some hiccups along the way.
Exactly. And that's where error correcting codes come in. These codes introduce redundancy into the data to help detect and correct errors. And here's the connection to Krotov's work. Many of these error-correcting codes can actually be represented as truth tables of Boolean functions.
Oh, okay. So by tweaking the Boolean function, we can actually tweak the properties of the code itself.
Exactly. And one crucial property we can influence is the code's distance, which basically measures how well it can detect and correct errors. The higher the distance, the more robust the code is.
Okay, so higher distance means we can handle more errors without losing the information.
Precisely. And what's great is that Krotov's construction gives us a way to create codes with specific distances, while also ensuring they're as efficient as possible, meaning there's no wasted information.
Wow, that's pretty powerful. So more reliable data transmission with less overhead, that's a win-win.
Exactly. And this is especially important in applications where reliability is paramount, like satellite communication or data storage, where even a single bit error can have huge consequences.
Right, that makes sense. So coding theory is one big application. But we've also talked about cryptography. So how does Krotov's work tie into the world of secret codes and secure communication?
Well, cryptography is all about protecting information, making sure communication is secure, and Boolean functions are actually at the core of many cryptographic algorithms
Okay.
for things like encryption, hashing, and so on. And the security of these algorithms really depends on the properties of the Boolean functions used.
Okay, so we need good Boolean functions to have good cryptography.
Exactly. And one key property here is nonlinearity.
Unlinearity, okay.
And that basically measures how well a Boolean function resists being approximated by a simple linear function.
Okay. And why is that important? Why do we want nonlinear Boolean functions?
Because linear functions are very easy to analyze. They're predictable. So if you're using a linear Boolean function in your cryptography, it's going to be very vulnerable.
Okay, that makes sense.
But if you use a highly nonlinear Boolean function, it creates a much more complex and unpredictable relationship between the input and output.
So it's like making the code much harder to crack.
Precisely. And Krotov's construction allows us to create these highly nonlinear Boolean functions with very specific properties, like being balanced or unbalanced, depending on what we need for the particular cryptographic application.
Oh, wow. So we can actually tailor-make these functions to fit our specific security needs.
Exactly. And again, his method ensures that these functions are as efficient as possible because there are no non-essential arguments.
Right. Efficiency is always important, especially in cryptography.
Absolutely.
Okay, this is all really impressive stuff. Coding theory, cryptography. But you also hinted at applications in machine learning. Can you tell us a bit more about that?
Sure. So machine learning is all about training algorithms to recognize patterns and make predictions based on data. Think about those algorithms that tell you what movie to watch next or what products you might like.
Right, they're everywhere these days.
Exactly. And one of the big challenges in machine learning is feature selection.
Feature selection.
Which basically means figuring out which variables, which pieces of information are actually important for making good predictions.
Okay, so it's like separating the signal from the noise, figuring out what really matters.
Precisely. And you can think of these features as the arguments of a Boolean function, where the output of the function is the prediction made by the algorithm.
Oh.
So if we use Krotov's construction to create Boolean functions with no non-essential arguments, what we're doing is we're ensuring that our machine learning model is only focusing on those most relevant features.
Got it. So it's like helping the algorithm to really hone in on what's important, ignore the distractions.
Exactly.
What are the benefits of that?
Well, for one, it leads to more efficient models that require less computational power, less memory.
So they're faster, they're leaner.
Exactly.
Okay, that's always good.
And by removing those irrelevant features, you reduce noise and you actually improve the accuracy of the model's predictions.
Oh, wow. So we're making the algorithm smarter. We're helping it make better decisions.
Precisely. And finally, using only those essential features makes the model more interpretable, meaning we can understand how it's making its decisions.
Right. That's really important, especially in areas like healthcare or finance, where we need to be able to trust these algorithms.
Exactly.
Wow. So Krotov's work, which started as this really abstract mathematical exploration, has these incredible applications in coding theory, cryptography, machine learning. It's really amazing to see how this all ties together.
It really is. It's a great example of how even in pure mathematics, there can be this very real, very practical value waiting to be discovered.
Absolutely. Well, this has been a fascinating deep dive. I feel like we've only scratched the surface, but it's been a really great journey. Thank you so much for joining me and guiding us through this really complex topic.
It's been a pleasure. Always happy to talk about this stuff.
And to our listeners, we hope you've enjoyed this exploration of Krotov's work. It's a reminder that math is not just about equations and formulas. It's about exploring ideas, solving problems, and uncovering the hidden connections that make our world tick. And who knows, maybe one of you will be inspired to make the next breakthrough in this field. So keep those minds curious, keep those questions coming, and we'll see you on our next deep dive.